Okay, Shannon, we're live.
Thank you.
Hi,
So
Shannon. This is Rita Baron-Wall.
Great. Welcome, Rita. Thank you for joining us. We will be getting going in about 10 minutes. So if you want to just turn off your webcam until I introduce you, then that would be great. Everybody
Okay, great.
has
And Shannon, can you hear me okay?
Yes.
Okay, all right, fine. I won't change a thing. Thank you.
Yeah, you sound great. Thank you, Rita. So thank you all for joining us this morning. We will be getting started here in about 10 minutes. And until then, we'll just show this. If you have any technical issues, please send a note in the chat window to organizers, and we'll get going here shortly. Thank you. Thank you all for joining us this morning. The webinar will begin in approximately 5 minutes. Welcome to the webinar this morning or this afternoon. We will begin in approximately 1 minute. I still see quite a few attendees joining. Thank you. Good morning and good afternoon, and welcome to the webinar today on clean nuclear energy for industry. This webinar is sponsored by GAIN, the Gateway for Accelerated Innovation in Nuclear, as well as Electric Power Research Institute and the Nuclear Energy Institute. Before we begin with our speakers, I would like to share a few details about our webinar. Thank you again for joining. If you do have technical issues that come up during the webinar time, please submit them through the chat option on the GoToWebinar control panel. You may enter all questions that you may have for speakers using the questions option on the GoToWebinar control panel. These questions can be entered throughout the webinar, and I encourage you to do so. We will address questions after each set of speakers, so we'll hear from all of our industry speakers, and then we will go to questions following those speakers before we go on to our speakers on advanced reactor technologies, and then we'll have an open general discussion at the end of the webinar. If we are unable to get to your question during the webinar timeframe, we will log all of those questions and follow up after the webinar has completed. We do expect the agenda to run approximately 2 hours, but the line will stay open for about an additional hour so that if we have discussion, we will have time to address additional questions and work with you as attendees. So thank you very much again for joining us today. I'd like to begin by welcoming our first speaker, Dr. Rita Baranwal. Dr. Baranwal serves as the Assistant Secretary for the Office of Nuclear Energy in the U.S. Department of Energy. Dr. Baranwal leads the office's efforts to promote research and development on existing and advanced nuclear technologies that sustain the existing U.S. fleet of nuclear reactors, enable the deployment of advanced nuclear energy systems, and enhance the U.S.'s global commercial nuclear energy competitiveness. Rita, if you'd like to go ahead.
Okay. Hi, everybody. Thank you, Shannon, for that introduction. I want to welcome everyone to the webinar. I very much appreciate all of you joining while we navigate through this new normal for us. Some funny things I want to share with you is, as we have been working from, many of us working from our homes, we're getting accustomed to working in pajamas and whatnot. And recently I've been on some video chats where folks have shown up in, or have seen video chats where folks have shown up in tuxedos and mentioned that, oh, well, they put a shirt on for the meeting, or they pluck their eyebrows for the meeting. So some interesting activity going on while we adjust to this new normal. I definitely want to thank GAIN, NEI, and EPRI for hosting this webinar. Very much appreciate us trying to proceed with our business and using the tools that we have at our disposal to continue to share our thoughts and the information that we want to get out there in public. So exploring integrated energy systems, looking at alternate applications for our nation's power plants, and supporting the development of advanced reactors are very important to the Office of Nuclear Energy in the United States Department of Energy. NE is committed to playing a positive role in our nation's operating fleet as well as the fleet of the future. And I have to share with you that I did get a sneak peek at slides that you're going to be presented today. And my favorite image of the deck is about halfway through the webinar. It really demonstrates a very unique application for our existing fleet and how it can and will hopefully contribute to our communities and impact the transportation sector. As I mentioned, we are operating in a unique environment at the moment. I look forward to a productive webinar. Very much appreciate your time and contributions. And although we're not face-to-face, please do use the chat feature that Shannon mentioned You're getting access to some folks that do not normally participate in our discussions, and so you're going to get some unique perspectives and an opportunity to ask them questions on some very unique applications. So with that, I will turn it back over to Dr. Gregson. Thank you.
Thank you, Rita. So yes, I did fail to introduce myself. This is Shannon Bragg-Sitton. I work at Idaho National Laboratory, where I lead much of our work in integrated energy systems. And so I am helping to pull this webinar together. Of course, we had hoped to meet all of you in person in a face-to-face workshop, which we hope to do at some time in the future. But in the meantime, we want to start this conversation. And so I wanted to step back and review our goals for today before we go into the detailed presentations. The primary goal for this webinar is to introduce end users of energy to the potential contributions of nuclear energy in meeting your energy demands. We have a wide variety of attendees today, ranging from the nuclear industry to non-government organizations, chemical industry operators, and a number of different people listening in. So I hope that each of you is able to garner some benefit from what you'll hear today in understanding how nuclear energy can meet more than just electricity demands. I also want to summarize to you the concept of integrated energy systems and what we mean by that and some of the potential, and allow industry leaders to share progress on non-electric applications of nuclear energy. I'm very excited today to welcome 4 different utilities to our webinar to share with you what they are working on at current fleet nuclear plants to produce electricity, but to also produce hydrogen. And as we look to the future, what they'll be looking at even further. So today I want to initiate a discussion on the requirements, considerations, and concerns for energy system planning at these energy use facilities. I encourage you to follow up with us if we don't have a chance to discuss some of those requirements. And this webinar is just intended to be one in a series. We plan to follow this up with other webinars moving forward on a regular basis, such that we can begin to better address energy planning needs across the board at many different facilities. So with that, there, you finally get introduced to me. As I said, I lead integrated energy systems work at Idaho National Laboratory from the Nuclear Science and Technology Directorate. So my role today is to introduce you to what we mean by that. What are integrated energy systems? So let's take a quick step back. When we talk about designing our energy systems for tomorrow, we need to step back and understand what goals we're trying to achieve and agree upon some of those goals holistically. In general, our energy systems need to be clean, non-emitting systems. They need to be affordable, so we know what that energy will cost today, tomorrow, and in the years to come. It needs to be reliable so that it's available when it's needed, on demand. It also needs to be resilient to weather events, to cyber attack, and various other things that we may not even be able to envision today. And they need to be sustainable. We need to think about where those resources are coming from and the impact of those energy systems on our environment and what the disposition path is once they've served their purpose. We also need to think about how that energy will be used. Now, many times when we think about energy system planning, we think primarily about the electric sector. But I also want to open that discussion to consider other applications, to consider what needs we may have to support industrial processes with high grade or low grade heat or steam, perhaps. What chemical products are needed to serve various needs? What are the intermediate energy products that might be considered in these processes? And are those energy demands constant, or are they variable? Or can they be flexed such that we can better accommodate multiple energy needs within an integrated approach? And then we can begin to consider what role each energy source can fill. Now, INL is the nuclear energy lab for the Department of Energy, and so we come at this from a nuclear perspective. What roles can nuclear energy fill? But we also look at the roles, the complementary roles of other energy generation technologies, namely renewables such as wind and solar and hydro, and fossil, particularly with carbon capture and sequestration, keeping in mind those clean energy goals that we set out at the start. So with that, I introduced the concept of integrated energy systems, which I do believe is a key opportunity across all of our energy use sectors. As I mentioned, many of our energy system planning activities look primarily at electricity. So we look at individual generators and how they contribute to the grid, how they contribute to meeting the demands every day. And much of our non-electric applications, industrial applications, have dedicated energy sources that support their needs. For example, combustion of natural gas or coal in order to provide the heat to drive industrial processes. What integrated energy systems do is they begin to take a step back and look at an integrated grid system and integrated comprehensive energy parks that allow us to maximize contributions from carbon-free energy generation sources such as nuclear and wind and solar, as well as fossil fuels with carbon capture and sequestration, in order to meet energy demands across all of these energy use sectors, electricity, but also directly coupling into industrial applications and meeting needs in the transportation sector as well. Now, you'll hear from 4 of our utility partners that focus in on hydrogen production today. We're looking much beyond hydrogen production, but hydrogen is a great entry point to some of these applications because hydrogen as an energy carrier can be utilized in so many different applications. It can be used in steel manufacturing, production of ammonia-based fertilizers, can be used directly to produce electricity at a later time, or in fuel cell vehicles to support our transportation sector, or hydrogen can even be combined with captured CO2 in order to make synfuels to drive many other processes. So I'd like to begin with that idea of utilizing our energy generation sources in unique and novel ways to meet these various energy demands. So today you'll get a chance to hear a little bit more about some of these initial projects in industry that are taking us to that next step. What do these systems look like in practice? What are the opportunities to inject new energy generation sources into some of these non-electric applications? So the laboratories, DOE has been working with current fleet operators for nuclear plants, utilities, and is supporting 2 primary public-private partnership awards to demonstrate hydrogen production technology on site at nuclear plants today. These plants will be putting steel in the ground soon, in the next 12 to 24 months. And I'm not going to say any more about that because I want you to hear that story from our utility partners and hear from them directly on what they are doing to accommodate these new approaches, this new paradigm for energy use, how they are approaching safety evaluation and regulatory approval for these processes, and where we go from here, starting with small-scale demonstrations and moving up to larger-scale applications. So I hope that you are encouraged by that and that we will be able to hear lots of exciting things throughout these presentations. So one thing I want to start is thinking that what our energy systems can provide is really quite different than what we do today. Nuclear energy provides a vast amount of clean energy today. In the US, nuclear energy provides 55% of the clean electricity in the United States, but it can do so much more. We can bring that abundant dispatchable energy into industrial applications as shown here on the right. We can bring that to production of clean water and make a desert oasis, or it can be taken to remote applications or regions that need energy but don't have ready access to the standard grid, don't have ready access to a number of different facilities that rely on diesel shipments from time to time. So I invite you to open your minds to that in how we can think about energy system planning in the future and how nuclear can and should play a role in that. So with no further ado, I'd like to introduce our first industry speaker who will open this session on nuclear industrial integration demonstrations. I'd like to welcome Dr. Ugi Otgam-Battar, who is a corporate strategy manager at Exelon Corporation. Ugi joined Exelon in 2016, and since then he has been working for Exelon's corporate R&D partnership program, focusing on early stage energy technologies, including clean hydrogen generation, energy storage, and technologies for repurposing the existing nuclear fleet. Ugi holds a bachelor's and PhD in nuclear science and engineering from MIT, with research experience in thermal hydraulics, computational materials science, and he's previously worked for R&D groups at EDF, General Electric, and Tokyo Electric Power Company. Ugi, I'll hand it to you.
Yeah, thank you, Shannon. First of all, is the audio okay?
Yes, we hear you great. Thank you, Ugi.
Okay, thank you. Yeah, I mean, thanks, Shannon, and thank you for the invitation and the opportunity. If you go to the excellent slide, please. To talk about hydrogen. So personally, I mean, like you said, I spend a lot of time, thinking about and working on hydrogen for Exelon Corporation. So it's a great opportunity to share our thinking from Exelon's perspective and take some time to talk about our recent projects on hydrogen and have an opportunity to discuss with the industry partners. If you go to the next slide. Yeah, this slide just gives an overview of Exelon as a corporation, and I wanted to highlight a few numbers here. On top right, the installed generation capacity. So we have about 32,500 megawatts of installed capacity, and I think everybody knows probably on this call, majority of that is nuclear generation. So I think probably more than 60% is nuclear plants, and I think we have 22 units in operation right now. But we do also have about 10 gigawatts of natural gas fired generation and some renewables as well, wind and solar. So that makes our fleet as one of the cleanest in the country. I also want to highlight, we do operate natural gas distribution businesses in some regions in the US. So Baltimore and Philadelphia regions would be where we operate those natural gas distribution businesses. So the reason to highlight these non-nuclear businesses is that when it comes to hydrogen, it's a cross-cutting technology. So we are seeing a lot of interest in application of hydrogen in the gas fired generation, gas turbines, as well as for the gas distribution business. So for us, hydrogen is not only relevant for nuclear, it's also relevant across the board. And as corporate strategy, we try to develop a broad strategy that's applicable to our core businesses. So next slide, please. Yeah, this map just gives a location of our operating units. So as you can see, we are heavily concentrated in the Midwest. I think 6 sites in Illinois, one of our key regions. We do have some plants in upstate New York, Pennsylvania, Maryland, and New Jersey as well. So if you notice where these states are located, these states are, they have competitive electric power markets, unlike some other states. So they're part of what's called PJM market. PJM is, I believe, the largest electricity market in the world. I think about 120 gigawatts of peak generation, and that means all of our nuclear plants are competing in this market and competing against all other sort of power generation assets in these regions. So a good way to think about it is a nuclear plant in Illinois is competing against a gas-fired unit in Pennsylvania. There is some transmission congestion charges, but that's the main principle for a single market there. So because of that, all of our nuclear plants are exposed to a market price in this market. And because of low natural gas price, we're seeing in recent years, the power price has been very low. So that puts a financial stress on all of nuclear plants in PJM and other electricity markets. And I think we've seen some premature shutdowns because of that market dynamics. I think the latest example is 3 Mile Island. So that was an Exelon owned operated unit, and the challenging market dynamics led to the closure of that unit. And again, that was a loss of another 1,000 megawatts of clean generation capacity. So with this market dynamics, Exelon is working very hard to save our nuclear plants and sustain them in the long term, to help with decarbonization efforts in the long term. So we've been engaged in several policy initiatives on state level, but at the same time, we are also exploring technology solutions to save our nuclear plants and enhance their value in the long term. So I'm here to talk about those technology related initiatives. Shannon, if you go to the next slide. Yeah, this just lays out how we are thinking about hydrogen for our nuclear plants as a repurposing mechanism. So on the top of this figure, you have carbon-free nuclear generation right now. That's feeding the electric grid and supplying electricity and nothing else. So as you know, nuclear is a primary energy source that's carbon-free, can be used to make other commodities other than electricity. But right now we're only doing, supplying electricity. So the first question we asked was, what else can we make with, this carbon-free, primary energy source? So number one there is a concept involving, hydrogen production from nuclear electricity using the electrolyzer technology. So one of the first things you can do with nuclear electricity is produce hydrogen on site and store it on site. So the question becomes, once you have this hydrogen on site, it's very difficult to store. And the question is, what do you do with the hydrogen? So number 3 there is indicating sort of the self-consumption of hydrogen for the power plant's own use. So as you probably know, nuclear plants consume a lot of hydrogen, and we are currently purchasing that hydrogen from big industrial gas companies. So there's an opportunity in the near term for us to make our own hydrogen on site and offset purchases from external companies. So that's what we are focused on in the short term. But going beyond that, there are scale-up opportunities for that hydrogen production. So number 4 is talking about injecting that hydrogen into a gas pipeline that already exists. So it's a great way to transport carbon-free energy carrier like hydrogen and use it for different purposes. So one interesting use case, and I think our APS will talk about it, is using blended hydrogen into natural gas for natural gas power plants. So when you blend hydrogen, if the hydrogen is carbon-free, that is decarbonizing your natural gas-fired generation. So there's a lot of interest in the industry to explore that, and big companies have technologies to burn hydrogen at various levels. Number 5 here is talking about supplying hydrogen to on-site users. So I think there are 2 interesting use cases here. The first one is green ammonia production. So the technology exists to produce ammonia, which is a key fertilizer ingredient, to make ammonia from essentially electricity. So you make hydrogen, and the hydrogen feeds into Haber-Bosch process, and so that produces ammonia. So that's an interesting use case for us because we are located in the Midwest and close to some key markets for fertilizers and ammonia, and there is a transportation cost advantage that we want to explore. But like I said, the ammonia production from electricity is an old technology. I think it was practiced in Norway during early parts of 20th century, and there have been green ammonia plants in operation for decades, and that's on the order of hundreds of megawatts. So it is a relatively mature technology. Going to number 6 here, Again, one of the scaling up even further beyond that, we could envision sort of supplying regional hydrogen market from nuclear produced hydrogen. So that's probably the longer term use case, but there are some new applications of hydrogen that's coming up. So like hydrogen use in transportation, heavy duty transportation sector and things like that are, experiencing some growth, and that's kind of interesting for us to explore. But again, for merchant hydrogen, there's already an existing supply chain, and we would just be adding supply to that existing market. So that's kind of interesting for us. Next slide, please. So yeah, and then we have taken some steps to explore this vision. So number 1, 2, and 3. So I talked about self-supply of hydrogen. So what we are doing with DOE funding and 50% cost share from DOE EERE, and working with this company called Nel Hydrogen and 3 of the national labs, we are installing a 1 megawatt electrolyzer, one of our excellence units. So that project is going along very well, and we are getting close to site selection at this point. And Shannon asked me to touch on safety. So again, we haven't selected the site, but so based on preliminary analysis, looks like the amount of hydrogen we'll be adding to the site is going to be minimal because the electrolyzers don't store a lot of hydrogen. So right now, the current strategy is to design the system such that we don't need license amendment review from the NRC. So that's our current strategy, and the unit is expected to be running in 2022. Next slide, please. Yeah, this is slide. I won't go through all of this, but this is showing our preliminary, economic assessment. So if you are interested in the details, there is a light water reactor sustainability program report on this analysis that should be available. But again, the bottom line is, for the economics of hydrogen production, the electricity price is very important. Lower the electricity price, the more competitive you are in terms of hydrogen cost. And the scale of production is very important, and the efficiency of the electrolyzer you're using is another factor that's very important. So yeah, looking forward to your questions and your discussion after this. Thank you, Shannon.
Thank you very much, Ugi, for introducing us to that project. It is definitely an exciting project, and I'm really looking forward to seeing where it takes us. Our next speaker is going to talk about another project to use nuclear energy for hydrogen production. They're taking a little bit of a different approach relative to Exelon. So I'd like to introduce Alan Shainwald from Davis-Besse Nuclear Power Station, which is owned and operated by Energy Harbor, which was recently First Energy. Alan has a Bachelor of Science from The Ohio State University, where he majored in mechanical engineering and minored in nuclear engineering. Alan currently works as a project manager in the strategic engineering department at the Davis-Besse Nuclear Power Station. And he has worked there since 2011, and he's been in this role since 2014. Alan is the project manager for the Light Water Reactor Integrated Energy Systems Interface Technology Development and Demonstration. Alan, welcome.
Hi, good morning. Hi, thank you for having me. That's a pretty good intro. I feel like I don't really have anything to add just about myself, so thank you very much. If you go to the next slide, please. All right, so I will be speaking today about our project to install a hybrid energy system that is capable of automatically diverting electricity from a nuclear power plant, namely Davis-Besse Nuclear Power Station, to a low temperature electrolysis hydrogen generating skid to create hydrogen. The objective of this project is to diversify and increase the revenues of nuclear plants facing increased competition from renewables and low-cost natural gas. I'm sure that line or something like that line will be parroted many times throughout this webinar today. So Davis-Besse Nuclear Power Station, got a little arrow over to the right in the map. It's located in Northwest Ohio, approximately 25 miles east of the city of Toledo, along the shores of Lake Erie. So some of the benefits of operating this hydrogen generation skid, this hybrid energy system at Davis-Besse Nuclear Power Station, by taking electrical power at the nuclear unit prior to going to the grid, you are reducing electricity costs. The inputs for hydrogen production that we are using for low temperature electrolysis are electricity and water. Those are things that we have existing utilities facilities for at a nuclear power plant, so makes it easy for integration and then scale of production. Our plant's relative proximity to key markets are ideal for reducing transport distances. Our location in Northwest Ohio is pretty well situated to some key major industrial hubs, as well as main transportation corridors, namely the Turnpike, I-80, I-90, I-75. And then the hydrogen that we'll be generating is from a carbon-free source. So that's something that we're looking to keep in operation, is these carbon-free baseload electricity plants at our nuclear units. Next slide, please. So this slide just gives an overview of where we are with the project in funding space. So we are still in negotiations to complete the award. Our project collaborators include Idaho National Labs and then 2 other utilities, Arizona Public Service and Xcel Energy, both of which will be presenting today. The project duration, once we entered the period of performance, is roughly 24 months. Next slide. Talk about hydrogen skid selection. So the equipment that we will be using is low temperature electrolysis. It uses polymer electrolyte membrane technology. This is a proven technology. It's been used commercially available. So using a proven technology will minimize risk to the project. We're really proving the concept of integrating this energy system into an operating nuclear power plant. So we're looking to be able to remove risk where we can. The equipment is to be containerized. That will allow us to have more of a turnkey solution. And that will also allow us to reduce the engineering efforts and then have a quicker implementation timeline than if we were constructing a new building, a new system from scratch. The skid itself that we're aiming for will use roughly 2 megawatts of our electrical output and consume roughly 2,400 gallons of water per day at maximum operating capacity. Next slide. This is just a quick overview of the modification process that we will take at a nuclear power plant. So biggest portion will be the analysis. We want to ensure that the effect the skid and the supporting equipment will have on the plant's operation is minimized, and we're going to have to address the design and licensing basis considerations. Ugi had a good point about trying to limit the amount of hydrogen that is on site. That is also something that we are looking to do by having minimal on-site storage and quick transportation off-site be a part of the project. And I'll touch a little bit more on my next slide about that. Other aspects, the electrical, the mechanical, and the civil design will all be kind of integrated to tie everything up and ensure that we're doing what we are in the safest means possible. Next slide, please. This is a preliminary top-down view of the site and our proposed modification of the facility for placement of a skid. So what you have is a Google Maps view, for just lack of better, of the Davis-Besse Nuclear Power Station. So over on the right, you have the power block. That is the containment structure, is the big white cylinder. Right in the middle is the switchyard. So we have our electrical tie-in coming from about that point. And then off to the bottom left of that picture is the proposed hydrogen production area. We're opting to design and locate the equipment such that the effect on the site is minimized. Just in terms of any sort of storage, albeit minimized to the extent practical, we're looking at siting it as far as reasonably achievable from the power block, just to eliminate as much of the concerns as possible. So, like I said, storage, transportation are going to be the items to be addressed. We do not foresee any issues with potential amendments to our license. However, that is all going to be addressed in the modification process. In addition, we're trying to design our electrical tie-in such that the effect on the plant is minimized. Next slide, please. So the skid itself will be automatically controlled in a manner to maximize revenue for the nuclear unit. So that's really going to be producing hydrogen during periods that have depressed electrical prices. Similar to a number of the Exelon units that were just discussed in the previous presentations, we operate in the PJM market. So it's a competitive-based market. And what I have over here on the right are some graphs that show the hourly locational marginal prices. And those are cumulative, just to kind of have a sense of what the day-ahead locational marginal price in dollars per megawatt hour is, at or less. So if you're trying to kind of pair the skid's operation, the capacity factor, to market prices of electricity, you can kind of get a sense of, all right, if I have a set break point, what is the capacity factor of my skid? That's something that will be looked at, and it is a goal of the project to ascertain that number and make sure that we have the skid operating in that manner. The numbers that I have on the slide over to the right are not indicative of what we have for the project, what we expect. It was just a clean 50% capacity factor number. So like I said, this is something that we're looking to have the skids being able to automatically follow grid prices and other variables that are input by the user to give us the maximum revenue possible. Next slide, please. So transport and consumer base. We are looking at creating, collecting, compressing, storing, and then transporting hydrogen off-site as part of this project. So since we will be creating hydrogen for consumption, we need to identify existing markets that do exist in the area. Like I mentioned earlier, our proximity to key industrial centers is a benefit of the project. However, there are existing hydrogen markets, and then we need to also help to cultivate the emerging markets. There's a lot of excitement out there as to what could come, and we're looking to kind of get into that excitement. So what we're doing is trying to leverage some local and regional partnerships for that, just given our transportation distances being relatively small for some key industrial centers. We do have a publicly available technical economic assessment for the area that shows industrial users of hydrogen and potential bulk hydrogen generation scenarios that are out there. Next slide, please. So in terms of scale-up project conclusions, that will be at the culmination of this entire project, be rounding off all the numbers to present as a business case, looking at, hey, this pilot plant, it operated in this manner. We had this projected revenue for set hydrogen production. Is this something we see feasible going forward? And preliminary conclusions have shown a positive return on investment if future scale-up activities are pursued. So our initial pilot plant is roughly capable of producing 800 to 1,000 kilograms of hydrogen per day, and that's at maximum operating capacity factor. And that only consumes about 2 megawatts of electricity. The Davis-Besse Nuclear Power Station has a nominal output of about 920 to 925 megawatts electric, about a 2,800 megawatt thermal load. So there is significant margin to our capacity, both electrical and thermal, and what we are capable. So we see that potential for scale-up is something to be excited about. And so we're excited to push forward with this project and just see where it takes us. That's the end, and look forward to questions at the end. Thank you.
Great. Thank you so much, Alan, for that insight. And I saw lots of great questions coming in. So I'll have a bit of a task to try to work through those here as we get to the end. Before we get to that, I'd like to introduce Molly Strasser, who is the Innovation Manager at Xcel Energy. She has spent over 18 years in the nuclear industry, including time at the Braidwood and Monticello plants within engineering and maintenance organizations. And her current focus is adopting technology to remote connect the power plant with workers, as well as identifying ways to repurpose nuclear power to support Xcel Energy's carbon-free goals. Xcel has really gotten out ahead of the curve on seeking carbon-free energy for all they do. So Molly, I'm interested in hearing more about it. Welcome.
All right, Shannon, thank you very much, and thank you to all that are on the webcast. I know I'm enjoying a brief glimpse into the personal and the business views as we go through and see work environments as we work from home. So I hope everyone is learning a lot about these integrated energy systems. Next slide, please. Next slide. So a little bit about Xcel. We are an electric and natural gas company, and we're committed definitely to the clean energy transition. We're based in Minneapolis, Minnesota, so we have long winters here in Minnesota, but we also have a presence in the Southwest as shown on the map. We have almost 12,000 employees and natural gas and electricity operations. Within the electricity operations, we have 3 units of nuclear, 2 sites, and that'd be Monticello and Prairie Island, both located about 45 minutes in opposite directions of Minneapolis and St. Paul. The capacity of those 3 units is approximately 1,800 megawatts electric. We are a regulated market. You heard from Energy Harbor with Davis Besse and Exelon. Those are not regulated. Here in Minnesota, we are, but we still compete against our other energy sources for the lowest cost to the ratepayer. So we want to make sure that we're competitive, and we cannot be leaps and bounds as far as cost goes above what other generation sources are. Next slide, please. So in 2018, we made a very bold statement regarding carbon emissions as a company. We have bold plans by 2030 to reduce our carbon emissions by 80%, and our vision by 2050 is to be 100% carbon-free. We were the very first large utility to announce such an ambitious vision. And we are working towards ways to meet those 2030 and 2050 goals. The path through 2030, we have a good solid plan. We understand how we will get there. But 2050 is a little more up in the air, and we're still working through that. We do need nuclear in the portfolio to meet the 2030 goals. Right now, our units are licensed to operate within the extended period into the early 2030s. We are exploring and potentially applying for an extended license, but that commitment has not been made yet. So we're still in the preliminary legwork of determining if that's the right path forward for our ratepayer here in Minnesota. For 2030, we have put out a proposed Upper Midwest Energy Plan, and that sets our path on how we'll achieve those milestones. We do view hydrogen as a potential way of meeting those 2050 goals, and that's something that we want to incorporate into our integrated energy system plan. Next slide, please. So here in Minnesota, we've got a wide variety of generation sources. We have windmills, we have nuclear, we have solar, and we have hydro. And based on congestion and planning within the Minnesota region, we are finding that having the ability to operate flexibly is something that the nuclear plants can offer to the market. And that helps us work together with renewables. Our focus with Xcel is to work together with renewables and not compete against them. So what used to be viewed as a baseload power source, which nuclear is a baseload power source, we're showing that we can operate flexibly. And what that means is that both plants are operating in the day-ahead market, and based on energy needs, we can be asked to ramp down to 80% power. All 3 units with Xcel are on the day-ahead market, and here in the spring and the fall when the energy is swinging, and we're also seeing impacts from people working remotely and the coronavirus results, that we are definitely operating flexibly more often. So this is something that we are offering to help benefit both the renewables and nuclear and working together, whereas previously we would have been just a 100% power source. That begs the question of what do you do with that extra 20% if we are regularly going down to 80%? And that's where hydrogen comes into play. Could we use that extra 20% instead of just downpowering, divert it to the hydrogen skid and create hydrogen for green energy consumption later down the road? Next slide, please. So as Alan mentioned earlier, we are part of a consortium with 2 other utilities. We're working with Energy Harbor in Ohio, and then also Arizona Public Service and the Palo Verde plant in Arizona. And the Light Water Reactor Sustainability Program through the Department of Energy released a funding opportunity announcement back in 2017. And this is a way for utilities and the industry to work together to move forward in ways that we could advance green or carbon-free energy sources. The Light Water Reactor Sustainability Program is focused in on advancing nuclear power and improving advanced nuclear reactor and improvements of the existing domestic fleet. So this is a way that we keep our current fleet of reactors working, make them economically viable, while at the same time we're looking at advanced reactor technology and how those could play forward. We look at this within Xcel as a way to keep our fleet of 3 units in play, and then working with renewables and combining into an integrated energy system. This also plays in with the flexible power operations that I just described at Monticello and Prairie Island. And the funding opportunity announcements, the research that is done through them needs to be applicable to multiple reactor designs, which is good for Xcel because Monticello is a boiling water reactor and Prairie Island is a 2-unit pressurized water reactor. So even within Xcel, we have multiple reactor design types where we could take advantage of the research and make sure that it is applicable across the 100 nuclear units in the United States. We've heard from Exelon and Energy Harbor about low temperature electrolysis. One of Xcel's focus areas is high temperature electrolysis. So low temperature electrolysis only requires an electricity source or feed from the plant. The next step in this would be high temperature, and high temperature takes steam from the secondary side of the plant and is a combination of steam and electricity to separate water into the hydrogen and the oxygen. This plays well with nuclear because we obviously have a secondary side where we could take steam from, and it really ties it together and works with the light water reactor sustainability. So high temperature electrolysis is a more efficient process. You get almost a third more hydrogen when you utilize steam to make or produce the hydrogen. And it plays well because we have the large secondary side on both of or all of our units. And it would be something that we could offer that's different than renewable sources with just an electricity source. Next slide, please. So as I mentioned, we are an industry consortium with 3 utility partners in the national lab. As part of the project that is going at Davis-Besse to do the 2-megawatt demonstration, Xcel's project scope is a technical economic assessment. So we're evaluating our future electric and hydrogen markets to determine the potential. We also are different because we're regulated. One of our plants is also near an Indian community, and so we've had some public relation type issues to work through in addition to the Public Utility Commission for Minnesota. In addition, the 2030 and the 2050 goals for carbon-free generation, we want to figure out a way that we could use hydrogen with our nuclear plants and really further that green, clean, carbon-free nuclear energy system and work with renewables in the future. And we're really excited about pioneering a new area. Nuclear is viewed as 100% baseload power, and we're learning that we can do so much more with our technology. And this really would pave the way for advanced nuclear reactors and identify ways of thermal extraction or ways to use the energy in different manners rather than just produce electricity. Near us, we have several economic sources that could use large amounts of hydrogen. Those would include refineries, which are just south of the Twin Cities. We have some proposed data centers coming in. We have steel reserves in northern Minnesota. And then the Twin Cities is a large urban area, so transportation would be another market that we would like to explore. Next slide. So going forward, we plan to complete the technical economic assessment and the investor grade report. We are thinking of what a future hydrogen pilot at an Xcel nuclear facility would look like. Again, we are really focused in on high temperature steam electrolysis and furthering that research. U.S. manufacturing of those type of electrolysis skids is not where low temperature is. So this would be a way to bring the manufacturing for the high temperature skids along at the same time that we're doing testing at a nuclear facility. The energy requirements for high temperature, again, are 10% steam, and that's clean steam, and 90% electricity. So we will have some technical and regulatory requirements to work through. We'll go through the evaluation that's required, in addition with working with the Nuclear Regulatory Commission to complete the modification for the future pilot. Going through the Nuclear Regulatory Commission or NRC reviews is not a new or special process. That would be something that we would have to do for several types of modifications. But we will tie them in, especially since we are making modifications to pull steam from the facility. And then the largest thing that we're looking for is development of partnerships for future pilots with downstream users. So I mentioned some of the ways or the uses in the local area, and working with the national labs to complete the technical economic assessment will really highlight where those investors might be and where we can develop partnerships to try out some additional technologies that would further a green and carbon-free future. Next slide, please. So like to thank Davis Besse and Energy Harbor. I was at a conference in January up in the Toledo area, and this is a bus fueled by a fuel cell, so fueled by hydrogen. And I took a picture and sent it back to my boss because I want to show that this is a real thing. It's not just something that we talk about in meetings or webcasts like we're doing today, but there are technologies and applications of that technology in use today. So this hydrogen bus is used in transportation. It's in use today. And thank you, Toledo and that area, for helping further the technology. But this is showing that it's real and it's active today. And with that, I will turn it back over to Shannon and look forward to your questions at the end.
Thank you so much, Molly. I really do love this picture and the just bringing this to reality that hydrogen as a transportation fuel is real, and we're doing this, and this is what this is about. We're not just talking about analyses. So thank you very much for those remarks. Our next speaker in this section is Jeff Brown. Jeff is a senior consulting engineer at the Arizona Public Service Company. Jeff has 30 years of experience in nuclear fuels and mechanical design engineering, and is currently the technical projects lead for the Strategic Business Services Organization at the Palo Verde Nuclear Generating Station. Jeff holds a Bachelor of Science degree in nuclear engineering and a Master of Science in mechanical engineering from Arizona State University in Tempe. Jeff, over to you.
Thank you, Shannon. Good morning or good afternoon, depending upon where you're at. Thank you for the opportunity to speak today. What I'd like to discuss is our efforts here at Arizona Public Service to explore integrated energy systems to support our long-term sustainable carbon-free generation for the state of Arizona. Next slide. Next slide. There you go. So a little bit about who we are. Arizona Public Service is Arizona's largest and longest serving energy provider. We started providing power actually back in 1884, long before we became a state. We provide power to over 2.7 million Arizonans. We have a staff of about 6,300 dedicated employees that ensure our vision or make further our vision to create a sustainable carbon-free energy future for the state of Arizona. We are also a wholly owned subsidiary of the Pinnacle West Capital Corporation, and also we are the operating owner of the Palo Verde Nuclear Generating Station. We own about 29.1% of its total capacity. We certainly don't compare when stacked up against Exelon or Xcel in terms of peak generating capacity. For 2021, we're somewhere around 9,300 megawatts of peak capacity. Part of that is our nuclear power, part is coal, which we'll talk about shortly. And then most of our generation right now is gas. Next slide. So while we don't stack up relative to total generation or generation capacity, we do have the largest nuclear power plant presently in the United States. We have nameplate capacity of about 4,200 megawatts electric. It's a 3-unit plant, and we have 7 participating owners, one of which, of course, is Arizona Public Service. So the owners receive power, and that power is distributed to 4 states, Arizona, California, New Mexico, and Texas. It's a very good operating plant. We typically produce between 31 million and 32 million megawatt hours of carbon-free energy each year. Next slide. So here in Phoenix and in the desert Southwest, we do have a lot of increased renewable generation. It continues to grow, in particular solar. And then on a day like we have today, where it's absolutely beautiful outside, 72 degrees, and the fact that a lot of people are home, as Molly said, telecommuting instead of in their places of business. We have a lot of solar generation and very little demand. So this increases the impact or the pressure on Palo Verde to curtail power output so that we can balance the system. So we have 7 owners, and each owner has a different business plan and a business objective, and they use the power and need the power in different ways. So the possibility of curtailing power, it can happen, but it's highly non-desirable at this time. So we are looking at alternatives to power curtailment. And a couple of years ago, we started talking with Shannon and the Integrated Energy Systems Program and became very interested in this particular approach as an alternative to curtailment, but also realized that production of non-electric commodities such as hydrogen or ammonia or others could also provide for other market-related opportunities. Next slide. So, in addition to the effects of renewable energy, APS2 has announced our clean energy commitments, and much like it is at Xcel, we have a carbon-free goal by 2050. The path is not completely clear as to how we get there, but it is very certain that Palo Verde is going to be a critical piece of that equation. Closer in 2030, we have developed our plan to achieve those goals. That will involve additional commercial development of about 45% renewable energy, and in combination with this, we're also going to eliminate coal by 2031. So again, a very important piece of all this is the sustained generation that we get from Palo Verde. Next slide, please. So as far as integrated energy systems go, we've looked and we believe that hydrogen is the fuel and or energy carrier that makes most sense. And our project going forward is focused on the generation, the storage, and the use of hydrogen. Next slide, please. So Molly mentioned here about our project with the Light Water Reactor Sustainability Program and our collaboration with both Energy Harbor and with Xcel. We've participated and sent in a proposal in response to the DOE Office of Nuclear Energy's funding opportunity to advance the integration of these systems with nuclear power. The program is structured such that there's two primary objectives. One is the development of the regional economic analysis for each of the respective participants, and then the other part of the project is to develop and advance these technologies to provide for economic and cost-effective hydrogen generation and its use in the various sectors. What specifically the project does is it helps work with the laboratory, Idaho National Labs, in advancing these electrolysis technologies, both in technology and in scale. So we can start in the kilowatt range and eventually get to the point where we're grown or help the manufacturers grow the system to the size where they're commercially ready. In addition, and as Alan alluded to, these technology demonstrations are designed to demonstrate that we can safely integrate these systems, and in particular when it comes to the thermal use or the high temperature systems, that we can safely integrate these into the nuclear power plants. So as part of those evaluations, it's critical that we look at the hazards associated with generation and storage and to minimize the risk. We also want to make sure that as we integrate these systems into the power plant, that we understand how they're going to react and interact with our primary and secondary systems and ensure that we are able to operate and maintain our plants within their original design bases. So Molly identified that they are looking at high temperature steam electrolysis, and most of the motivation for going to that type of technology is really focused on its improvement in efficiencies. And from what we've done so far at APS and for Palo Verde, we recognize that for hydrogen to be a necessary element or a critical element of what our long-term program is, we have to be able to generate hydrogen on a cost that's comparative, if not less than what we produce hydrogen through steam methane reforming and through renewable generation. And it's our opinion right now that in order to achieve those goals, we have to be at a high temperature application. So as the project that we've discussed here with LWRS and funded through the DOE Office of Nuclear Energy, as that progresses from low temperature to high temperature, Palo Verde's goal is to expand on the high temperature system and introduce the reversible high temperature system, particularly since our goals are targeting capacity or storage, so that we can provide an alternative, like I said before, to curtailment of the Palo Verde plant. Next slide, please. So we envision, there we go. So we envision a reversible high temperature steam electrolysis system that's built on the same technology that Molly discussed, but it also allows for a reversible process where the hydrogen generated through this, we'll call it stack, could be stored in hydrogen storage tanks. And then when the market conditions are such that the price of power has gone up and we have a greater demand on the grid, gas from the tanks can then be pushed back through the same stack as if it were a fuel cell to put additional power on the grid. There are other alternatives to this type of capacity related approach, but this is one that we believe holds promise, and our discussions with some of the manufacturers suggests that this technology may be ready in time, and that's what we're contemplating our demonstration to be based on. Next slide. So I'm also happy to announce that we've had a number of discussions amongst the Palo Verde executive leadership team, and a lot of excitement around the use of hydrogen, both in terms of capacity, but in addition, we as the APS fleet are looking longer term and trying to figure out what makes sense in terms of additions or replacements for our gas generation assets in order to achieve our long-term carbon reduction goals. What you see here in the picture is the APS Red Hawk facility. It's a 1,100 megawatt combined cycle plant, two 2x1 units, and in the far distance you can see Palo Verde. So our executive leadership team believes that we should start the process, or at least put the proposal together to look at the process of converting or blending hydrogen into these natural gas plants. And the long-term vision that I have is that if we're able to produce high-temperature hydrogen very cost-effectively at Palo Verde, we're able to transport that or pipe that over to the Red Hawk plant, and we could use that as a clean, carbon-free generator when demand needs it. Another interesting attribute here about this Red Hawk facility is it's a zero liquid discharge facility, which means that all of the water that we process here has to either go up in the environment or has to remain on site. And to facilitate that, we have a very large brine concentrator that is an excellent source of carbon dioxide. So as part of the proposal that we're contemplating putting together here and submitting, we're going to look at taking the carbon dioxide, mixing it with the green hydrogen for the purposes of producing synthetic fuels. One other potential application, given the potential demand in the future for a regional gas transportation, is the use of hydrogen fuel for transportation. Next slide, please. So just a few considerations. Again, I think I've mentioned that hydrogen capacity and cost are the most important items to address to make this cost effective. Again, the high temperature electrolysis efficiency is needed, I think, in order to get the price or the cost parity that we seek. We need to support, particularly for the high temperature systems, we need to support manufacturers in their ability to begin producing this technology at scale. And I need to make sure, and this is, I think, where the Light Water Reactor Sustainability Program will be supporting, is to ensure that these systems are flexible enough such that they can react on a daily demand situation to help provide that function for curtailment. Storage is an issue that we're addressing, and we'll without going into too much detail, there is a potential for regional large-scale storage in salt structures that we're going to consider, and that would be part of a downstream opportunity. As both as Oogie and Alan and Molly all stated, these integrated systems where we're placing hydrogen in and on around nuclear facilities. There's a lot of safety concerns, but we need to ensure that we remain in compliance with both all of our licensing and design bases. And the last point that I think particularly applies for this integrated energy systems is looking for policy that supports clean generation and can help bring price parity among all the different energy sources. So with that, Shannon, I'll turn it back over to you.
Thank you all so much for giving us insight to these really exciting projects that are being developed and that are moving forward to build these engineering systems. This is a really exciting opportunity for the nuclear industry, but industry in general, and that's really what we want to convey here. With so many cities and states and utilities and private companies seeking to reduce their carbon footprint, these types of activities are so incredibly important in injecting clean energy into these processes. We are going to pause here for a moment to address some questions that have been coming in, and you guys are great. We have so many good questions that have come in, and so I'm just going to select a few here and there and maybe remark on a few of the comments. One that I did want to personally address was a comment with regard to hydrogen, fuel cell vehicles, buses, forklifts. Absolutely, these are out there, they are available, they are being used. However, when we take a step back and look at where that hydrogen is currently coming from, most of that comes from steam methane reforming methane cracking, where they utilize fossil fuel combustion to provide the heat to drive those processes. And then in the methane cracking itself, it emits CO2. So these processes are by no means clean. There's significant emissions. And so looking at hydrogen in a different way to introduce hydrogen to the market that uses clean energy sources and does not emit CO2. This is where we're really trying to look at impacting some of that carbon footprint across the board. So again, just selecting a few questions here for clarification. Oogie, I'll first go to you. There's a question about the efficiency of hydrogen production using these approaches with the low temperature electrolysis specifically. And looking to the larger hydrogen use projects that you introduced, how much will be needed for those projects? What does that hydrogen market look like now, and in the future, how is that growing, and how will we be able to meet those?
Yeah, thanks, Shannon. That's a great question. I think a good number to remember when it comes to efficiency of these electrolyzers is, it takes 50 kilowatt hours of electricity to make 1 kilogram of hydrogen. So $20 per megawatt hour electricity price translates into $1 per kilogram in hydrogen price, and that itself is a very competitive price in the hydrogen market. So depending on that and the electricity price, I think different markets kind of open up. I think Idaho National Lab did some study on, if you converted, a certain number of nuclear plants entirely to producing hydrogen, how much additional supply are you adding to that hydrogen market? I think the answer was something like, a single nuclear plant producing hydrogen at a full capacity was, if I remember it correctly, it was like 5% of the hydrogen supply in the US. Another analysis we did is, if you take the current production of hydrogen and assume that all of that hydrogen was produced by electrolysis, that's equivalent to 73 gigawatts of electricity. So, and that is expected to grow to 180 or 190 gigawatts, I think, in the next 10, 15 years. So I think there's an opportunity to use, electricity to make hydrogen to meet those, future demands.
Thank you so much, Ugi. I appreciate that answer. I'll direct my next question to Alan. And this is a great question. We talk so much about electrolysis and making hydrogen, but we don't talk as much about the oxygen co-product. So what is the plan for that oxygen co-product from the electrolysis? And then a follow-on question, as you build this electrolysis plant on site at Davis-Besse, is there a security risk that will be introduced to the plant either during construction or operation to produce hydrogen?
All right, so 2 questions I will address. First one being what to do with the oxygen that will be produced. So currently we do not have plans to actually collect the oxygen, store it, and transport it. In doing so, if we were to collect it, compress it, put it into transport trailers and take it off site, that is all something that would cost money to do or have to be factored into a price. And currently we do not have plans for that. Now, if something were to change in the future, we would definitely be able to evaluate that. If there were a user that would be looking at using the oxygen, that is something we would surely evaluate. However, just releasing it to the atmosphere is our current plan. The second question was in regards to security risk from the hydrogen skid being installed on site or during the construction portions of it. So it's a great question. That is something that we are looking at. We are ensuring that we have our security organization engaged in the design phase of this project. That's very similar to all projects that occur at a nuclear power plant. I'm not really going to get into too much detail on that. I do apologize. However, that is things that are being addressed in the modification design process. So.
Excellent. Thank you, Alan. I'll direct a question to Molly now, and I think this is a really good question. As we move from low temperature electrolysis that's driven by electricity to the high temperature electrolysis applications that now take steam from the secondary side of the plant to drive some of those processes, what is the expected efficiency penalty on the nuclear plant when you do pull some of that steam for HTE applications?
Great question. Thanks, Shannon. So what we would be looking at is 10% of the energy coming from steam and 90% coming from electricity. So we have thermal losses in our plant of 1 to 2 megawatts that we have at any given time. So even if you have a larger scale hydrogen production facility, the impact is not that significant. Now, we would do analysis to make sure that we understand our margin and our design bases for pulling that 10% steam off of the secondary side. But in general, we could perhaps do an uprate to the plant to get that extra thermal energy that we would need and still maintain the output electricity-wise for the plant. That will all be included in the modification, selecting the right point to extract the steam as to not upset the thermal efficiency or the thermal process on the secondary side will be part of the evaluation, and also how we control that and the manner in which the steam is diverted from the plant to the electrolysis skid. So in summary, it's not a large amount of steam, and we've looked at it from a technical perspective and don't anticipate technical challenges. We will work through the modification and the regulatory work to prove that all out before we implement.
Thank you, Molly. I'm going to direct this next question to Jeff, but it is certainly one that all of you could address based on the different energy markets that your plants operate within. Negative hub pricing was mentioned several times during the presentations. In what ways have your organizations been affected by state and national policies which promote renewables, but in many cases sideline nuclear? So Jeff, I'd like you to take that one first, perhaps, and the impact of policy on how decisions are being made at APS.
You know, one thing that I should mention is that Palo Verde and APS are in a regulated market, just like Xcel is. So much of the power fluctuation and the impacts on pricing have more of a minimal impact on us. But nevertheless, we are responsible for ensuring the best value to our ratepayers. So our involvement with the energy imbalance market has some positive effect on minimizing the overall losses, such that we transfer those or are able to pass savings and minimize losses into our ratepayer.
Oogie or Alan, would one of you like to speak to that from a deregulated market perspective?
Sure. Thanks, Shannon. And negative price is something that we have seen in the past to a greater extent, but it's been sort of, getting less and less in the last few years. If you look at the underlying reason for why the negative prices are happening, I think it's really because of the congestion price component in the LMP. And that happens because of the transmission line constraints. That could happen because of renewable energy resources over generating in certain regions. I think in PJM, wind generation is the main one. So I would say that it's a combination of renewables not being scheduled optimally and constraints in the transmission line. But again, that's something that we are seeing less and less of in the last few years.
Great, thank you, Oogie. I am going to halt this Q&A session for the moment. We will have additional discussion time, but I want to make sure that we have opportunity to take that look, a glimpse into what is coming soon for nuclear technology, what is on the forefront. One of the last comments or questions that I see in this list is regarding how we might incorporate higher temperature reactors to applications such as high temperature electrolysis. And absolutely, that is something that is of interest to the Department of Energy and to the many different developers of advanced nuclear technologies. We recognize that efficiencies are certainly increased when we produce heat at higher temperatures and can inject that into these industrial processes. There's a lot that we can learn from these initial projects that we've just gone through on how we take nuclear energy into industrial applications, whether via electrical interconnection or thermal interconnection, and we can use upgrading of heat from these lower temperature reactors to get to some of these high temperature processes. And so that's something we're working on from the laboratory side, and we're working hand in hand with industry. So with that, I do want to move to our next speaker, who will talk a little bit about that nuclear energy innovation. Where are these advanced reactor technologies going? When will we see those on the market? And how can we begin to incorporate these systems into the energy system planning and decision-making in industry? So I'd like to introduce Dr. Everett Redmond, who joins us from the Nuclear Energy Institute, where he is a senior technical advisor for new reactor and advanced technologies. He's responsible for NEI's programs and policy efforts to support development and commercialization of advanced reactor technologies. Everett has a PhD from MIT in nuclear engineering. So Everett, I'd like to welcome you, and I'm looking forward to hearing from you as well.
Thank you, Shannon. I appreciate it. Can we go to the next slide, please? Thank you. So I'm going to take a few minutes today and thank all of you for joining the webinar today. Very much appreciated, and thank the speakers that went before me for laying a great groundwork in terms of what hydrogen can do and using nuclear for generating hydrogen. I'm going to take a few minutes today and discuss some of the exciting work that is going on right now in the advanced nuclear space. I'm not going to talk about the details of the various technologies, but rather talk about real programs and real projects that are underway. We can save the discussion about various technologies for a future webinar. Next slide, please. The first thing I want to highlight is an exciting new program that Congress created in fiscal year 2020 appropriation space. It's the Department of Energy's Advanced Reactor Demonstration Program. This program has two parts to it: demonstration and risk reduction for future demonstration of reactors and risk reduction for future demonstrations, both of these through public-private partnerships. The demos will be supported through public-private partnerships and support the design finalization, licensing, and construction of 2 advanced reactors with the goal of having them operational within 7 years. $80 million per project in federal money is being put forward in FY20 for that. And then the risk reduction program will help prepare future companies for future demonstrations. And there'll be 2 to 5 awards given there. Allocations for this year were $30 million for that. It's expected that both of these programs will be multi-year efforts. And the funding opportunity announcement for this program will be coming out probably at the end of this month, end of April. And we expect the winners for these projects to be announced sometime by the end of the year, maybe. Department of Energy has done a request for information earlier this year to get some information on this program and has set up a website that has some more information on it. And as I said, the FOA will be coming out shortly. This is very exciting because it's going to help bring some new products to market. Now, what I'm going to do is talk about some demonstrations that are actually beginning to occur now. So next slide, please. So the future here in terms of advanced nuclear will bring forward a wide range of sizes. So we'll have the traditional large reactors like we have now, greater than 300 megawatt electric. All of the speakers that spoke before me are talking about reactors that are currently operating well above 300 megawatt electric, up to a gigawatt in class size. So advanced reactors going forward will also fill that market. And when I say advanced reactors here, I mean reactors that are both water-cooled and non-water-cooled reactors. Then we'll also have reactors in the range of less than 300 megawatt electric, and we refer to those as small modular reactors. And again, they can be anything from a water-cooled reactor to a non-water-cooled reactor, and I'll touch on a couple of those projects going forward. Then there's another class of machines that we refer to typically as microreactors. Now, I've just said here that's typically maybe 1 to 10 megawatt electric. There's no set definition for that, so they could be a bit larger than that too. But that's just kind of what we think about right now. So there's a really great opportunity coming forward here in terms of some of the different sizes. And what's great about this is that they'll be able to fill different markets. I'll touch on one market in just a moment about remote locations, but also powering retired generation. So there's a lot of generation capacity out there right now: coal, natural gas, wind, solar, nuclear. And some of the non-nuclear capacity is rather small in size, anywhere from maybe even 90 megawatts electric up to a few hundred megawatts electric. And so some of these new designs that are coming in the nuclear space will be able to help replace those generation sources when they retire. So now I'm going to talk about some projects that are occurring right now. Next slide, please. So the first one I'm going to touch on is NuScale and UAMPS. So NuScale Power is finalizing their design certification application with NRC right now, and that design is 12 modules of 60 megawatts each. So 12 small reactors, 60 megawatts electric each, for a total plant size of 720 megawatts. The image you see here is an image of a potential NuScale plant. As I mentioned, the design certification application is under review with NRC right now, and approval is expected at the end of this year. The design certification really means that NRC is going to approve the design, and then a company, a utility, can reference to that design when they decide to go forward and build it. And in that front, we have a project, the Utah Associated Municipal Power Systems, looking at NuScale and planning to build that at the Idaho National Laboratory site. UAMPS is currently a utility, municipal utility that does not have nuclear generation capacity. So this is great because they're looking at expanding into nuclear as part of their clean energy portfolio. And in fact, this is part of their clean energy power project. And they already have they already have a site use permit for property at Idaho National Laboratory, and we would expect that plant to be operational around 2026. The great thing about NuScale, in the sense of having 12 small reactors of 60 megawatts each, is that that provides an enormous amount of flexibility in terms of how that plant operates, because you can adjust each one of those, and they are able to ramp the whole plant up and down in power level quite rapidly as a result of that flexibility they have. So it'll be a great opportunity to integrate well with other renewable sources. If I could go to the next slide, please. So I mentioned microreactors previously, and microreactors, again, looking at sizes anywhere from 1 to maybe 10 megawatt electric or a bit larger than that. They're being looked at for a number of different applications, actually. Remote locations, so think, for example, Alaska, northern Canada. You see an image here of an Arctic village. Also remote locations, say domestic military bases in Alaska or other places that need secure, reliable power on site. And then looking at possibility of a mobile microreactor. So a microreactor that can be transported easily, moved into a location, set up and become operational within a few days, and then when mission completed, taken down and shipped out within a few days as well. This also could be great for disaster relief in certain areas where you lose a lot of power and you need to bring in some power. A mobile microreactor could have the possibility of doing that. And also then thinking about microreactors and other locations, they have the potential to be used very well for, say, mining applications or other things where you don't have ready access to the grid and you need to bring in power there, and bringing in electric power from the grid is just not doable. On the mobile microreactor front, there's a demonstration being planned by the Department of Defense. And in fact, the Department of Defense earlier this year, the Strategic Capabilities Office within DoD announced awards for 3 companies to begin developing mobile microreactors. That project will culminate in a demonstration of a mobile microreactor, which we expect to occur around 2024, also at the Idaho National Laboratory. So right there you see between this project and the previous one, NuScale, 2 very different size reactors and real projects that are beginning to move forward here. And so some very exciting stuff coming. So let me move on to the next slide. And what I want to touch on is another project here. Again, this is in the microreactor area, microreactor size, and this is the Oklo Aurora Fission Battery. So Oklo is a commercial company designing a microreactor right now. And their idea is design would have it generate about 1.5 megawatt electric. So kind of perfect size for a small village, Alaska, northern Canada sort of thing. Looking at actually 20 years before refueling that machine. And it could generate heat and electricity both. Oklo just submitted an application to NRC earlier this month and submitted that application to NRC, and it's currently undergoing acceptance review by NRC. And they expect to do a demonstration at Idaho National Laboratory, and I would expect that to occur also in the 2024, around that 2024 time period. Again, this image right here you see is image of the Oklo fission battery reactor. And if you're interested in that, I encourage you to take a look at their Facebook page or take a look at NRC. Also, same is true for NuScale project, because there's public meetings that you can take a look at if you want to. But all of these projects that I've just talked about, the Oklo project, the NuScale project, and the mobile microreactor projects are real things that are going to culminate in reactors being built here in the not too distant future. One for commercial generation of electricity, that's the NuScale plant. The other two being kind of demonstrations, although the Oklo machine absolutely will generate electricity, future applications for that. And then also we have that demonstration program that the Department of Energy is undertaking this year, which will then lead to future demonstrations. And at the end of this year, we could see anywhere from 2 to maybe 7 to 9 awards given to companies to begin developing designs, 2 of those being demonstrations in the 7-year time period or so. Let me move on to the next slide and kind of wrap this up for a second. So, as we've talked about here briefly, and I'm just giving you a quick flavor for what's going on in the nuclear space right now. And as I said, we can have a future webinar to touch on more of the details of the design and everything. But these reactors that are being designed now can be used for multiple purposes: electricity generation, hydrogen production. Molly made reference to advanced reactors when she spoke. They can be used for generating heat for industrial uses as well, in addition to hydrogen generation, but there's many industries that need heat as well. And then we have a variety of designs coming. So to summarize, really the bottom line is the future of clean energy will bring new reactor designs and new applications. And I look forward to any questions you may have either here or offline. Thank you. Turn it back over to you, Shannon.
Thank you very much, Everett. I appreciate that little glimpse of what is coming down the line and when those advanced reactors may be available to meet the needs of so many of these applications. And we'll have a later webinar that focuses in on some of these technologies to dive a little bit deeper into that area. This time, I'd like to welcome our last speaker for this webinar, and that's Dr. Andrew Sauter. Andrew is a senior technical executive in the Advanced Nuclear Technology Program at the Electric Power Research Institute, or EPRI. Andrew leads EPRI's new advanced reactor portfolio and previously coordinated R&D on light water reactor accident tolerant fuel R&D, and also managed applied research on used nuclear fuel management and advanced nuclear fuel cycles. So Andrew, I will hand it to you. Welcome.
Thanks, Shannon. And I will have a mercifully short presentation, mainly focused on touching on 2 general themes and topics, I think, to close out at least the presentation portion of today. Next slide. So really what I wanted to speak to from a perspective at EPRI, since we are an end user facing organization, we are chartered for public good research, but we do that through supporting primarily electric power utilities around the world, in the US and around the world. And we touch on or interact with about 80% of the world's nuclear operators. In the United States, every nuclear operator is a member of EPRI. So from that perspective, I wanted to start with the first theme I think that's important to keep in mind about the future of nuclear and its role and really its importance. Next slide, please. And that's really what does the future look like for nuclear? And if I knew, I would probably not be in this job. I'd be, I guess, in Las Vegas or doing the stock market. But instead, the only thing I can say with certainty about the future is it's uncertain, which is pretty clear. But uncertainty really in and of itself is a useful organizing theme, and I think a good way to think about the value that nuclear current plants as well as future plants and new missions for those plants can bring for electricity as well as the energy infrastructure more broadly. So I think if we go down through these questions, just ask these questions, what will the price of natural gas be in 2030? Well, you know, most people would suspect that the price of natural gas will be fairly stable into the future, but we really don't know. What will the price of carbon be? Will there be carbon policy in place? Again, since that is generally driven through policy and a political process, that's highly uncertain and can also change from administration to administration every 4 years, every 2 years with a congressional election in the United States, for example. Another important factor when we're looking at nuclear is to not forget that competing technologies are also innovating. And so, and as you heard, the utilities operate a portfolio of technologies. They're not just in the business with nuclear. And so it's always important to keep in mind that other technologies will continue to compete with nuclear, and so must be kept in mind. So for example, natural gas with carbon capture sequestration technology at scale certainly fills the same similar niche, if you will, that nuclear does in terms of its low carbon footprint. Similarly, renewables with grid scale energy storage options are also a strong competitor for nuclear in terms of filling dispatchable low carbon energy resources. Again, it becomes a question of, you know, does carbon capture sequestration truly come online when it's needed? And will grid scale energy storage really be available when it's needed? Again, unknown, but if not, having nuclear in the portfolio certainly addresses and hedges against that uncertainty. And then finally, I think it's really important for us to not fool ourselves into thinking we really know what the future will be. There are always unknown unknowns. And think about the next shale gas revolution. Going back about 12 or 13 years, when I started at EPRI, on the right here, I'm just showing one of our projections or looks into the future using one of our models at the time, which was called PRISM, where we were trying to project what a future energy mix might look like to reduce CO2 emissions to I think it was 2005 levels, or to keep them there. And if you look at this mix, again, you see coal being still dominant. And if you recall at the time, coal was the dominant energy generator in the United States. And that the technology that was seen as keeping coal online was carbon capture sequestration. Natural gas, if you recall, back pre-shale gas, was seen as a relatively high-cost fuel and highly volatile. And so the projections, according to what we knew at the time, saw gas actually being squeezed out of the equation. And then finally, nuclear was poised to fill the gap. And again, this is at the tail end of the so-called nuclear renaissance in the United States. And so we were also very bullish on the future of nuclear as a technology as it existed then in largely advanced light water reactors to fill the gap. And so you can see just from a year from this, things changed very dramatically, and our projections now show an entirely different portfolio mix, with natural gas now basically eating everybody's lunch. And coal, many retirements already, and expected continuing retirements of coal generation, other than the newer advanced coal plants. So I think that's one thing to keep in mind is, again, as good as we think we are looking into the future, we really don't know what the future market might require. Certainly having as many options and as flexible options as possible is important. Next slide. The second theme I just wanted to touch on was the idea that it's really important to understand what a customer, in spite of that uncertainty, might want and need based on what we have learned to date with over 50 years of operating nuclear power plants commercially. These are really self-evident, but I think it is useful to just kind of put them out there for perspective purposes. First of all, what's required for commercializing a advanced reactor or any technology or product is it's got to be mature. So in the area of nuclear, we need demonstrations, and again, that's the direction we're moving in. So very positive outcomes. Those technologies also need to be compelling in that they really need to offer new attributes and capabilities relative to the current technology. Otherwise, it is really a hard sell to conservative businesses like large utilities. Why should they take the chance on a new technology when we already know we can operate nuclear power plants safely, reliably, and under economic conditions, we can even do so in a competitive manner. And then lastly, obviously, just because it's a shiny new technology doesn't mean it's not subject to the rules of the road in terms of being competitive. If it's going to be commercial, these technologies do need to compete, and given the uncertainty, they likely need to compete on a robust basis, regardless of policy, in many regards, out to the future. So cost and value from products, reduced costs in construction, well-defined deployment timelines, and certainly the idea of providing new access to markets and products is an important one. Now, that's just one half of the equation, and often this is the half that most people think of in R&D space, the technologies themselves. But at EPRI, we see really the customer is as important, and if not more so, than the technologies themselves. And so for the customer side of things, really what they need is they need to understand the technology. So they need to be both informed and engaged in the process. And again, you're seeing by today very positive signs, a number of utilities in the U.S. actually stepping up to the plate and going beyond just being informed and engaged, but actually demonstrating new technologies. They need to believe, so they have to see evidence of performance. So again, this is where demonstration comes into play. And so really the recent announcement of the DOE Advanced Reactor Demonstration Program really is an important step forward in achieving that with new advanced technologies. And then finally, just because the technology is offering something doesn't mean it's going to be compelling unless the customer needs it. So this is really where the business case of the customer comes into play. And again, today's been great because you've heard straight from the horse's mouth, if you will, the various needs and drivers for why these utilities are starting to look at alternative missions and products for their existing nuclear fleets. So next slide. And last slide. Okay, so that brings me to, as I promised, a short but sweet presentation here, kind of a summary of these two perspectives brought together. Really, so the technology developers really need to understand customers and markets for their products. And perhaps even more importantly, the developers and vendors, they need customers to begin with. They need to identify those customers. So again, that's why having utilities step up like APS, like Xcel, like Exelon, Energy Harbor, really offers a chance for them to understand what a potential future owner-operator wants and needs. Now, the customers, for their perspective, and again, I say customers because owner-operators in the future may well be utilities, but also with alternative energy products, they may well not be. So customers and other primary stakeholders need to have an interest in understanding the technology landscape and what's coming down the pike. So again, that's why there continues to be a need for outreach and avenues and ways for folks to understand. That's why the GAIN series of workshops and this kind of interaction is so important. But customers not only have a role in purchasing the technology, but in the nuclear space, it's really important to have early engagement from the customers from the standpoint of requirements to help inform the design process. And then finally, obviously advanced reactors do offer compelling options, and so they really need to, because they have to compete with other technology solutions that may be coming down the pike, and they need these options to also provide the flexibility in uncertain and changing energy markets. And really, this is just more the same of what we're facing today. As you heard, the need to curtail generation. Wouldn't it be better to do something with the heat than to turn down the plant, but instead actually divert it from some other revenue generating product? And so I'll conclude with a shout out and shameless self-promotion perhaps of what we're trying to do at EPRI, which is to bring together the technology developers with the future owner-operators, currently focused heavily on the electric utilities because those are who our primary members are. But again, it's really important to bring in other potential end users to help develop a flexible framework that takes into account these new missions as well as the manifold number of technologies options. And so that's what we're trying to do with this owner-operator requirements guide, is to provide that framework. This has been revised once. It's in its second revision, and that number is all you would need to look it up. Google it. It's publicly available, and we're interested in working with the community to perhaps do more with this or do our part in terms of aligning the customer with the technology developers in the future. So with that, again, appreciate the opportunity to share a few words and appreciate everyone's attention and participation today. Thank you. Thank you, Shannon.
Thank you so much, Andrew and Everett, for giving us that insight to advanced reactors and the potential that is coming down the line. I do want to have a few more questions addressed before we close out today, but let me just make a few general remarks, particularly as we come off of Andrew's presentation where he's talking about engagement of customers and understanding customer needs by engaging energy end users, non-traditional users of nuclear energy now, while so many companies are developing these new advanced reactor designs. We can really begin to inject some of the requirements of the chemical industry users, of hydrogen production facilities, bring in some of the requirements of those systems, bring in the constraints of those systems, and understand both your needs and your concerns about how nuclear energy can support your energy demands as you go forward in each of your businesses. And on that note, I'd like to go to one of the questions that came in. And I suppose I'll direct this one first to Everett, but that many of you can begin thinking about this as well. Given the public's concern with nuclear energy, how will we reassure people of the safety around producing other products such as hydrogen at nuclear sites? To the average person, introduction of hydrogen production at a plant may seem irresponsible, introducing an explosive element perhaps. So how do we go about informing the public about these new opportunities and the safety associated with these opportunities? Everett, do you want to take that one to start?
Sure thing. Thank you, Shannon. Well, the demonstrations that I talked about are a good way to start that conversation with some of the advanced nuclear machines. And there's an opportunity here. A lot of the advanced technologies have more inherent safety than the existing fleet reactors, build upon that safety case. And so that conversation is ongoing with the Nuclear Regulatory Commission. And I think the industry is open and upfront about its activities here. And I think that will help continue to do that. In terms of the hydrogen issues particularly, I defer to the other speakers. I would note, though, that hydrogen, as some of them may mention, is used currently at many, if not all of our sites for some chemistry uses. So let me pass the conversation over to some of our previous speakers.
Yes, would anyone else like to remark on that, please? I'm not sure who to point to first.
This is Alan. I would kind of just parrot what Everett just said there with hydrogen is currently used at pretty much all nuclear sites in varying levels based off if it's a boiling water reactor or a pressurized water reactor. So, you know, the actual nuclear sites are familiar in dealing with and maintaining storage of hydrogen on site. In addition, I'd say that just the culture at nuclear sites, you want to use that existing culture of, you know, being very upfront, open, honest with the safety aspect and just knowing what is important about your job that you're doing at the site. I think just kind of keeping that same attitude, that same workmanship, and just applying it to this is going to be a great combined thing that will instill some confidence in the public.
And yeah, this is Ugi. I just wanted to add to that. I mean, hydrogen is a existing industry. I mean, there are existing supply chains for hydrogen and established players. So right now, I don't know if you see the track on the highway, companies like Air Liquide and Air Products, they are shipping and moving and transporting large quantities of hydrogen currently. And there's an existing supply chain and existing codes and regulations, and there's a Hydrogen Safety Council that we are starting to have conversations with. So again, it's a mature industry, and there are established safety protocols and processes, and we are sticking to and sort of complying with all of those regulations in addition to the nuclear regulations from the NRC.
Yeah, Shannon, this is Jeff. I'd like to add kind of what Ugi was just getting there too. We have existing licensing and design basis requirements that apply to all types of, we'll call them external threats. So, hydrogen is comparable to other, threats that could impact the plant. So we would evaluate it consistent with the requirements that we apply to any other type of design event.
Excellent. Thank you all. And somewhat of a follow-on to that, I'll direct this question to Molly with regard to the NRC. And I think NRC regulations and approvals really come into play mostly for the thermal integration when we're beginning to tap into the secondary side of the plant. What NRC regulations on hydrogen production or integration to the secondary side of the plant exist, and how are you approaching that with the NRC?
Thanks, Shannon. So within our modification process, we use the 5059 evaluation, and that guides us through when we need to ask the NRC for permission to make specific modifications to our plant. And that 5059 evaluation process is built into every modification we do. And in some cases, the modification does not require NRC approval before proceeding. But in the case of tapping into the secondary side, we will go through that normal process and determine how much interaction and how much approval we need from the NRC. We are also doing outreach. We plan to talk with our regulators and the regions on what our plans are, just so we don't surprise somebody with, this is our plan. We want to site a hydrogen or an electrolysis skid on the site. We want to make sure we're upfront on what our future plans are regarding that. So there is existing framework for moving through the modification process, the 5059 evaluation, and that framework exists, and we will be utilizing that. And I don't open it up to Alan and Jeff and Ugi if they have any other comments on that.
Molly, this is Ugi. And yeah, I mean, that 5059 is the current framework that we are aiming to utilize. And yeah, I mean, like you said, and that's an established process and a framework. And once we have a site selected, we will be going through that process.
Excellent. Thank you. So many questions coming in, and I'm trying to scroll through and address them as much as possible. We focused a lot on these demonstration projects on low temperature electrolysis and the vendors for those low temperature electrolysis units. With regard to the high temperature electrolysis systems, whose technology is being considered? What is at the forefront? What are we looking at there? Molly, since Xcel is looking at HTE, do you want to comment on that? And I invite others as well.
Could you go through that question again? I didn't catch the back end.
So we talked about low temperature electrolysis and PEM electrolyzers that will be deployed initially in the initial demonstrations at Davis-Besse and at an Exelon plant. What vendors are being looked at for high temperature electrolysis at this point in time?
Okay, thank you. So as part of the FOA process, there is an emphasis on U.S. manufacturing. So we have looked at, in conjunction with Idaho National Labs, on what vendors are in the United States and what state of manufacturing readiness they are in. Some of the ones that we've looked at include Oxeon, Fuel Cell Energy, Nexceris. We've talked with vendors like Bloom. We're also aware of some vendors in Europe that have manufacturing capabilities much larger than what currently exists in the U.S. Idaho is doing testing of some of these electrolyzer skids and stacks. That information is going to help inform longevity of the stacks, manufacturing processes that could be optimized. But we really want to work in conjunction with U.S. manufacturing, if at all possible, to help pull that process along. Obviously, we want to keep jobs and job security here in the U.S. So if we can approach this in a combined fashion and work with somebody here in the U.S., that's our goal. The vendor has not been selected. We are definitely going through research and evaluating all of those options, and we appreciate the support from INL.
Thank you so much, Molly. I see that it is noon Mountain now, so we've been going about 2 hours in this webinar, and your questions keep coming. This is fantastic. I know many of you probably need to drop off for your next series of meetings, so let me just make a few remarks, and then maybe we can take a couple more questions. This session, this webinar session, as I mentioned as we started, is just the first in a series. We plan to have many follow-on webinars. So this webinar is recorded and it will be available on the GAIN website on the workshops tab as soon as we can get it up there. And the slides that have been presented today will also be made available. So should you have questions, comments afterward, please go there, direct the questions via GAIN or to the contacts on each of these particular presentations. I also want to say that some of those future webinars are currently in development. If you have ideas for those, please send them to us. The next one in the series, which will probably be in about the mid-May timeframe, will focus in on applications of small modular reactors and microreactors in remote applications. We've already got a speaker lined up to tell us about the history of nuclear and the potential future of nuclear in Puerto Rico. We'll also be adding some others to that list as well. And as I mentioned earlier, we'll also focus a webinar on telling you more about some of these advanced reactor technologies and what their capabilities are, how they differ from current fleet, and what the opportunity space is. For those of you on the energy use side of this, I do encourage you to begin that conversation to help us understand how we incorporate your needs and your concerns into these advanced reactor designs. So at a future webinar, I will also invite you to come and speak on that webinar to tell us about those needs. And in the future, we hope to be able to do this in person in a workshop platform. Right now, we're all getting very used to these webinar activities, but it doesn't replace that face-to-face interaction, and we hope to welcome you to one of those in the future. So with that, let me go to a couple more questions. If you have to drop off, like I said, this will be available. But I want to address just a couple of additional comments. One is with regard to private investment in nuclear and in the development of these new technologies. I would like to invite comment, and I'll direct this to Andrew and Everett. Can you comment on the status of private investment in nuclear and the over $1.5 billion that has been invested in nuclear technologies by venture capital. Andrew, would you like to take a crack at that?
Sure. Well, I would say that's one of the remarkable things. If you look globally at the status of advanced nuclear technology, it is the private investment, and in some regards, within the last year, we have seen several national programs move away from their previous efforts in the advanced reactor area, and so in many regards, I think the private approach, the public-private approach here in the United States, also in Canada, and also the UK, has really actually provided a more robust approach, perhaps, now that we're seeing the developments elsewhere. And I would say that that is one of the probably the things that is different about this time, and why I believe, at least, that there's been so much energy and interest, is you are seeing the private investor start to, at least the ones with the patient capital, come to the table and say, yes, this is something worth investing in. Now, in terms of specifics, I'll turn it over to Everett, who in all likelihood deals with this sector much more than I do. So Everett, why don't you pick up the rest?
Okay, thank you. Yeah, the private investment is really quite impressive, and it continues to grow in this particular area in advanced nuclear. Just at NEI alone, we are a member organization, so companies join NEI. I've got about 20 developers that are members of NEI, the bulk of which are small, privately funded companies that are, working on designs. Oklo was one that was mentioned. They're a privately funded design. They've taken advantage of a number of the GAIN voucher programs that have been out there, but the bulk of their work is being done under private investment. NuScale and the others, the government, the public-private partnerships that are occurring here that I talked about doesn't mean the government's paying for it. Those are cost shares with private industry, with the companies that are putting money in, matching what the government's putting in. So there's a huge investment here and a growing investment. It's really very impressive. And the number of companies I mentioned that are members of NEI, that doesn't cover the entire landscape, because there are, and I can identify another 5 companies at least that are out there working on advanced nuclear in the US and Canada, and then more worldwide.
Thank you both for that. A similar question relating to investment, but on the side during the operation. Some developers are offering different business models in which they act as the owner-operator and can offer power purchase agreement structures to streamline adoption. I'd like to invite someone to comment on that. Again, perhaps Andrew or Everett, speaking to the advanced reactor and new build applications. How does that potentially streamline the adoption of some of these new nuclear technologies for some of these non-traditional users, heat users, or those that might want to have these as dedicated power systems on their site? Andrew?
I'm sorry, Shannon, I missed the first, this is part of the technology. I missed the first part of that, of the question.
Sure. So we're talking about business models. So as more advanced reactor developers or new technology developers are coming up, they are offering different business models where they may be the owner and operator of this power system, this energy system that works with power purchase agreement structures with the end customer, right, in order to help that adoption, to speed that adoption. Can you comment on how those work?
Sure. Yeah. So obviously, I think one of the big concerns with any new technology, especially in this space and with the recent history of problems with completion of projects, is the risk factor. And so the question is, who wants to be an early adopter or first adopter? And so, what one thing I've been impressed with or have enjoyed hearing are some of the different, another part of the innovation space is the business model space, right? So I have heard of at least one or two developers that have proposed an alternative model, as you had said, where rather than, just being a vendor and selling the product and, and then leaving, they would actually continue to own the nuclear unit and possibly even be the operator. And so in that regard, it basically takes the risk, the nuclear risk, if you will, away from the customer and maybe places it where it's better managed by someone who's more comfortable with it. So so in terms of like the power purchase agreement, essentially it's very much in line with an existing business model, and I think that would very much fit an existing customer's plans and scheme. They would not have to be part of the nuclear drama, if you will, if they're just in essence purchasing either power, heat, or both, or some other product. So that's one part of the business model. Also, another one that I think is even emerging, has already emerged, where you will see, again, we use the term owner-operator. You heard that the Palo Verde station has 7 owners, but it has only one, operator, which is APS. That is a business model that may well, continue to evolve as well, where you basically, maybe someone is willing to purchase a plant, but again, they're not comfortable, or not, their business plan is to become an operator. And so you have one of the existing operators step in to actually be the operator of record. And we're seeing that, I believe, with the UAMPS, where Energy Northwest is currently considering being the operator for that new UAMPS plant. So there's many different ways to skin the cat here in terms of the business model, and I think each one is unique, and it'll be interesting to see which one may play out. But I think they do offer to take the risk and put it in another place where it's better managed. I think it comes down to risk management in terms of making a business case attractive to a customer.
Thank you so much, Andrew. I think that's a great note to end this on. I know I have a tremendous number of additional questions. I do see people dropping off for other meetings. So what I'd like to propose is that we will take these questions, we will send them out to the speakers, and we'll address them and create this Q&A blog of sorts that can go along with our webinar record. There's really some great topics here. I see some suggestions for follow-on webinars, roles of hydrogen and energy storage. Absolutely, that's something we want to discuss. Microreactors and how these designs are being developed, etc. So at this point, I will close this webinar for today. I thank you all for your participation, for hanging in there for over 2 hours, and I definitely see a lot of interest here, and I encourage you to participate in future webinars. I'm really excited about bringing more and more clean energy into all aspects of our energy use. And I welcome your questions. I welcome your recommendations in many different areas. So please reach out to us. Let us know your thoughts. And I look forward to meeting with you again, both via webinar and future workshop applications. Thank you so much, and have a wonderful day.